So what does all this have to do with anything in reality? We talked earlier about how E shows up a lot in nature. And when we're looking at exponential growth and decay in naturally occurring things like populations, this is the essential formula we're looking at. Notice growth and decay, they're exactly the same except for this K goes from positive to negative, where we're literally losing a percentage of something every time, or we're gaining a percentage of something every time. You already know that A is the initial value, what we start with from the y-intercept, right? T is time in years. Okay, so if we're given something that we're working with months, then we're going to have to convert that to the decimal. And K is a constant that represents the rate of continuous growth, typically a percent as a decimal. Okay. So when we're looking at something like this first example, in 2000, the world population was estimated to be 6.124 billion people. In 2005, it was 6.515 billion people. Because we're starting in the year 2000, right? I could say 2000, 6.124, and then 2005, 6.515. But I don't want to mess with these crazy x values. The study started here, so we're going to convert this table and think of it as year 0. When we first started paying attention to whatever phenomena was happening, we were at 6.124. And then in year 5, after following it, 6.515. Okay, and I want to figure out K. So when I use my equation, y equals a e to the k t, I'm just going to plug in my values. My initial value, 6.124. Keep e. I don't know k, but I do know that in 5 years it had gone up to 6.515. Once we set that up, we're going to solve just like we normally would. Isolate the exponential by dividing. 2, 4. Okay, 6.515 divided by 6.124. Gives us 1.0638 e to the k times 5. Because it's base e, we're going to take the natural log. And the natural log of 1.0638 is approximately, instead of k times 5, I'm just going to write 5k because that's how we're used to looking at it. 5 by 5, and k is approximately, take the natural log of 1.0638 and divide that by 5.01237. Okay. So we have our k value with the same number of decimal places that we typically use, but earlier I said it's typically a percentage as a decimal. Well, if I convert that, then we know that our rate, right, we move it twice, is about 1.237%. Okay. I could cut that off at about 1.2, so it's a little easier to deal with, but if we're going to be the most accurate, then we need to carry around as many decimal places as we can. So when it asks, when will the world's population reach 7.5 billion, I'm going to come back to my formula, and I don't know when, so we're trying to figure out t. They gave us 7.5. Study started still in the year 2000, so we keep the 6.124 E, but now I know K, so we're going to go get that 0.01237, and we're multiplying that by T to solve. And we follow the same process. Divide to isolate. E to the 0.01237 T is approximately equal to 7.5 divided by 6.124, 1.2247. I've got base E, take the natural log, and the natural log of 1.2247 approximates 0.01237 T. Okay. I'm just going to leave it there. I don't want to figure that out yet because I'm just going to divide. And I know that T is about, we've arrived at these numbers through estimations. It doesn't make any sense to leave them there. And out of context, if I ask, well, how many years have gone by? Oh, the natural log of 5 divided by 2. It doesn't make sense to communicate that way. So here, we're definitely going to go ahead and calculate 0.2247 divided by 0.01237, and we get 16.386, so approximately 16.4 years. Okay, which, when? And we started with dates. Okay. So if we started in 2000 and we're asking when this is going to happen, and I know that's going to take about 16.4 years, so we can safely say sometime in 2016, probably about halfway through the year, would be a reasonable prediction. Okay. Now, what about the other way around? Okay. Logistic growth, when we talk about log growth, there's our logarithm curve, right? Again, can be used to describe a lot of naturally occurring phenomena. Okay. So if we know that this models the population of fish in a lake, okay, their population changes over time and it changes in this way. When we graph it, I can see that there's a horizontal asymptote. And the first thing they ask us to do is find it. Well, think about our graph. This is our years that go by. And this is our population of fish. Okay. So the number of fish in the lake is going to change over time, but the lake's not getting any bigger. Okay. So that has implications on the population of the fish in the lake. Okay? When it asks about the horizontal asymptote, when we look at it, we can tell it's happening somewhere in between here. And if we pay attention to the equation, we can tell exactly where that asymptote is. Okay? So I'm starting with 1880. And whatever we're dividing by down here, when I look at this multiplication of e to the negative, so we know that makes division. So the bigger this gets, the more we're dividing e by, the closer it gets to 0, means I can ignore this and I'm left with just 1880 divided by 1. So the horizontal asymptote is 1880. Well, what does that represent in the situation? And when I look at the graph, it's a little bit easier to tell, but this tells me that the population of fish will never exceed 1,880. Okay, it's going to do everything it can to get right up close to that, but that's where it's going to kind of level off. We may hit 1881, right? It may exceed it a little bit, but never significantly. It's always going to try to seek that balance at 1,880 fish. Okay, so when will it reach 1,875 fish? Well, I'm just going to plug that in. And it looks gross, but it's not so bad. 1875 equals 1880 over 1 plus 1.42 e to the negative 0.037 t. Okay. Well, if I think of this as being over 1, we can multiply 1875 times 1 plus 1.42 e to the negative 0.037 t equals 1880. Okay. I'm not going to distribute that through there because I'm trying to get t by itself. So we're just going to go ahead and start undoing. 1875, 1 plus 1.42 e to the negative 0.037 t equals 1880 divided by 1875, 1.0027. Okay. And because we have the benefit of calculators that'll let us do this, we're gonna write down all of our steps, but we're gonna save the calculation for a little bit. So we're gonna take 1 away, right? And then we're gonna divide by the 1.42, right? So let's do all of that at once. Minus 1, divide by 1.42, 0.019. So e to the negative 0.037 t equals 0.019, 2 zeros. Okay. Take the natural log. And then at this point, you can already see coming that we're going to divide by this negative 0.037 to get t approximately equals the natural log 0.0019 divided by negative 0.037. 169.3487. Okay. So when I look at my lake, from the time we started, they didn't give us any dates or anything, right? And if I look across, I can't get 1875 out of this. My graph is too small. But I can tell that it will take approximately 169 years to reach 1,875 fish in the lake.